Klopp, and now we are going to learn about sparse networks estimations. Please go ahead.
Thank you, sir. So as I'm very last speaker, I think it's a good point to thank the organizer for this beautiful workshop on behalf of all the participants. I learned a lot this week. It was really exciting workshop. Okay, so my talk is about sparse. Of course, yeah, well, and other speakers. I learned a lot. Beautiful talk, really. We discussed with some colleagues with like very exceptional speakers because it was very easy to follow, even in topics that we are not really working in. So people really made an effort to learn us something. It was really great. Okay, so my talk is about sparse network estimation. And first of all, so it's based on several work joined with Sasha Tsebakov, Nicolas Verzelen, and my PhD student, Solène Gauchet. And as we had many talks and like different topics where we have graphs limit, graph fonts, just to fix the ideas, my talk will be, so from statistical point of view, we observe a network. We assume that networks comes from a model, that means that it's a realization of random graph model. And we want to learn something about this unknown model, particularly parameter, if we run parametric model, or something else. So so what I'll discuss is model-based statistical analysis of networks. Okay, and so there is like very important line of works in statistics, which is trying to fit what we observe in practice, the real-life networks pre-model. I think many people here are also interested in this question. And so I'm also in parametric models are probably the most popular that has attracted a lot of attention, at least in machine learning and statistical communities, is the stochastic block model, right? I assume that everyone is familiar with it. Just to fix the notations that I will need for results. So we have n nodes, they are partitioned in k groups. And then, so each node is associated to a community. So, so community Z of I. So that will be the index function here. And then this parameter, this index function, either we can see it as a parameter to be estimated. So we want to learn the communities for each node. Either it can be viewed as a latent variable. So there are these two approaches to the model. And so on top of this index function, we have the matrix Q. So this is symmetric K times K matrix, which provides us the intercommunity H probabilities, right? So if you have a matrix, two vertices are connected with probability Qij, which depends on the communities. And so, so there are different reasons why this model is very popular. Of course, it's easy to study, right? This model is popular because it allows us to generate graphs with community structure, and many real life networks have community structure. But also probably there is some more fundamental reasons, because it can be like a very good basic approximation units for more complex models. So it's quite standard approach in statistics. So I have my data, probably the tree model is very complex, but let's approximate it to something easier, and that probably I can make good predictions on something quite reasonable from this simple approximation, like linear regression. So this somehow justify why stochastic block model is so popular in statistics. And so what I'll consider, we can also consider a slightly more general model in homogeneous random graph model, where we observe an adjacency matrix, right? And then we assume that each Aij is a Bernoulli random variable with parameter theta ij. And then we have matrix theta 0, which contains theta ij. And so this is the matrix of probabilities associated to the graph. And so we observe a graph, we observe the adjacency matrix, and what we will want to learn or estimate is this matrix theta 0, this matrix of connection probabilities, right? So in statistics, we are mostly interested in the sparse case. Why? Because real life networks were sparse, right? And for this inhomogeneous random graph model, there are different ways to define sparsity. There is this one, which is used a lot in the literature. We assume that the subnorm of matrix theta 0 goes to 0 when n goes to infinity. This forces kind of sparsity is quite homogeneous, right? For instance, we're not getting halves and so on. There are other ways of defining sparsity in this model, but maybe more adequate. But for this talk, I will use this definition, which is quite common. But many of stuff that I'll present can be extended to more general definition of sparsity. Okay, and so I'm interested in a very basic statistical question. I have a single observation of my graph, a single observation matrix A, and I want to estimate this matrix theta 0 for this single observation. Okay, and so as we are in statistics, one of the important questions is the question of minimax rate of convergence. So if you heard already talks on statistics, probably you have seen already what is it. So why they are important in statistics? The minimax optimal rate of convergence is the best rate that any estimator, any method can achieve the problem of estimation that we are looking at. And usually, so how it is defined, this minimax rate. So we take the infimum over all possible estimators, over all possible algorithms, and we take supremum over all possible parameters. So here, for instance, this is all matrices for stochastic block model with k communities and sparsity rho n. And then we're interested in the behavior of risk of any estimator. And then, of course, we need to choose a metric to measure the risk of our estimator. Here, the result is the Frobenius norm. And so in the Frobenius norm, the minimax rate of convergence for this problem are known for the stochastic block model. So here we have two parts. And actually, the interesting part is only this one. Why? Because this part, rho n squared, corresponds to a very sparse case when rho n is smaller than 1 over n. And this is the case that we know that the null estimator, that means that zero matrix, is minimax optimal. So this case is not interesting because I put everything to be equal to 0 and I'm optimal. So nothing to do in this case.
Does the result hold only when rho n is going to 0?
I'm sorry?
Does it result hold only when rho n is going to 0?
Yeah, so here rho n is a parameter. I assume rho n depends on n.
So even rho n is a constant, still the variance is going to 0, right?
Yeah, sure, yeah. So rho n constant is the dense case.
It's still going to 0.
Sure. Yeah. But it's normalized, right? Right. Sure. And so this is rate for the sparse case. It depends on rho n.
So why are you not dividing by rho n? Like if there's sparse, why is it 1 over n squared?
You mean the risk?
Yeah.
Wow, you can divide by rho n. Just another way to write it. But this is the minimax optimal rate of convergence for this class of matrices. I fix rho n, I fix k.
So I think it probably means by rho n squared because of the square norm. But if you divide by rho n squared, you just get log k over rho times n.
Yeah, but you know, rho n depends on n, right? It goes to 0, which means I divided by something that goes to infinity, my risk.
Yeah, it's just that we would expect n times, sorry, n squared minus n times rho n to be 0 anyway, right? In the matrix. No, I'm just saying we would expect only n choose 2 times rho n many edges, so n squared rho n edges.
Rho square.
N squared times rho n edges.
Yeah, this is where, yeah. If you assume that all the entries are uniform, yeah.
Yeah, order n squared rho n edges.
So what we're saying is
put differently. Yeah. Suppose we would just estimate it by 0. What would our error be?
By 0.
Is that basically your question?
This is the error. This is the error. Just 0, this is the error. And this will be dominating in the case when row n is smaller or equal to 1 over n. This is why we cannot deal with this case.
So the first
So
term
this is the
describes
error of a null estimator.
the first term describes how much better you can do compared to estimating by 0.
Yes. Not only comparing to 0, but this is the best what we can achieve in this problem. We cannot beat it. It's the infimum over all possible estimation methods. It's like we cannot do better for this problem. And actually, it's not that bad. Let me explain a little bit more. So as it's not mentioned, rho 1 equal to 1 corresponds to the dense case, right? And this what actually was difficult to get this right dependency on rho 1. Because if you deal with dense case, actually it's not that difficult to prove this rate, but to get a good dependency on rho 1, it was non-trivial. But if you
People don't understand.
I think the confusion is people don't understand your twiddle. Your twiddle means bounded above and below by a constant.
no.
A multiplicative.
Rho 1 it's an upper bound on the subnorm.
No, your twiddle in this equation
Oh,
means
sure, yeah.
theta of.
Yeah. There is two constants which are independent of rho n and k, such that
Okay, and now if
Release.
people want to divide each side by rho n, they are welcome to do that.
yeah, sure, yeah. Oh, okay, I got it. Yeah, so it means that we have like finite sample upper bound and finite sample lower bound, and two constants which are independent of dimension, whatever. You can divide by rho n. Sure, okay. Thank you, Christian. I'm happy. Okay, so let me somehow elaborate on the rate. And so if you suppose that rho n is equal to 1, that means with one dense case, the result has been obtained before. So in this very nice paper by Gao and co-authors. And so as I mentioned, so in this case it will be very this one, right? And it has two parts. Right. Actually, each one of these parts is quite easy to understand. So the first one is called, it's a really classical non-parametric rate in statistics. Why? I think that we know the labels, right? If we know the labels, the only thing that we need to estimate is that Q times Q matrix, K times K matrix Q, right? We have K square parameters to be estimated, right? And now we observe our GCC matrix, which is n square. So number of observations proportional to n square. So number of parameters to be estimated divided by the number of observations. This is why it's classical non-parametric rate. But we don't know the labels. And this is why we have this clustering rate. So if I have n nodes and I need to label them with k communities, I have k to the power n possibilities. And this is exactly the log of k to the power n divided again by the number of observations, which is proportional to n squared. So both rates were quite easy to understand. Non-parametric rate, which comes from estimation of matrix Q, and clustering rate, which comes from the fact that we don't know the labels. And the tricky thing was somehow get the good dependency on sparsity, because once a matrix is sparse, like rho 1 goes to 0, and so a rate like this, it's not meaningful, right? Okay, so good. So we have this minimax rate of convergence, which yeah.
Now, in your min-max, given how this is set up, you could use examples that a matrix which has one entry of rho n and all others 0. So what if instead you would define rho n as the average entry of your matrix instead of the largest one? Maybe plus some assumption that the largest one is not too much larger. Would you get better rates?
As I mentioned, actually, probably it's not the optimal way to find the sparsity. Is I understand correctly your question?
Yes, so I wonder if you define sparsity different, could you get better min-max rates?
Yeah, for instance, one way that I think it's better for this problem, we take the L1 infinity norm, like the subnorm of L1 norms of columns, divided by n. So ask this goes to 0. This is another way to find sparsity. Everything will go through.
That's the maximal degree?
Like it allows you to not be too homogeneous between the nodes, but when everything will go through, and so we'll get the same rates. So I think they are good rates. Then of course they depend on the norm. So they are known for Frobenius norm, for cat norm. For cat norm, the bad news. The adjusted matrix is already minimax optimal. But then of course we can think about other norms and probably somehow. This is for Frobenius norm, and the minimax rate to converge are also known for the cat norm. Okay, but I agree with this notion of sparsity property is not the ideal one. Personally, I prefer this one. Sounds like more.
For that one, you have to say.
I think we get the same. Yeah, I didn't try really each line. Oh, I'm quite convinced. I'm quite convinced. Only thing is, I'm sure that upper bound will be the same. I never tried to the lower bound, but the lower bound essentially is the same as for the dense case. And so the sparsity doesn't really play a role there. So I think it's, I will not like say cut my head. It's not true, but I'm 90% sure that it's the same rate. Okay, so this is nice, but so we want to estimate the matrix, right? And so we want a method which allows us to estimate the matrix. And the bad news here is that this optimal rate can be achieved by the least square estimator. And that means that we need to minimize over all possible labelings. It means so we have k to the power n possibilities, and the algorithm will scale exponentially in n. We don't want it.
Sorry for interrupting you again, but if I remember your paper correctly, it was not quite least square. You had to do something with knowing the largest entry of the matrix or something.
It was argmean. Indeed, we needed to know the yes, but
right.
It doesn't change the minimax rate because we fixed the class with rho n.
Oh, you now know your rho n. Okay, if you don't know rho n, then it's a different issue.
Well, actually, no, because I'll show more recent results where you don't need to know rho n, and you can be minimax optimal. So it's almost.
So now you know that the standard least square without this constraint is still min-max optimal?
No, I don't know that. I know that variation approximation to the Emily is minimax optimal.
Okay.
Much better because you can compute it. I never tried the least squares, but as if we tried very hard with Sasha and Nicola, I don't want to go through it again. Okay, so the problem is that we cannot compute the least squares because it's an exponential number of nodes, and so. Okay, and so so the next question was, so what can be achieved in polynomial time? So what can be done in practice? And actually, for quite a long time, we believed that actually this is one of the cases when we have what's called polynomial computational gap for this problem. That means that the minimax optimal rate of convergence cannot be achieved by the polynomial time algorithm. And so the next question was, what can be done in polynomial time? And so, for instance, one option is to use the hard threshold estimator. It's actually hard threshold estimator. It's really related to the universal singular value estimator by Chatterjee, except that we can improve his rates by substantially. And so essentially, if you go for the similar estimator, we'll get k over n rate, rho n k over n rate, which is not that bad, at least in this setting, which is reasonable. Usually we assume k small, right? So with quite simple estimator, we can get essentially quite optimal. We replace log k by k.
Can you define the estimator?
Yeah, sure. Yeah, it's really universal singular, so except with so have fixed the threshold. So you take the adjacent matrix, you take the singular value decomposition, right? Let me write it that way. And if in the stochastic block model, we at most rank k, right? And then we are doing a hard threshold. Let's mean that we'll cut. So we'll only keep the singular values in this decomposition. which are larger than something which is not other thing that the spectral norm of an error. So just the spectral norm of centered Bernoulli random matrix. So we need to cut the level of a noise measured in the spectral norm, and then we can prove that the rate which we'll get is actually this is not surprising because this is the rate for low rank matrix estimation. Okay, this rate, except for rho n, which is difficult to get. Because for low rank matrix estimation, you get the variance of a noise. And here, here essentially problem comes from the Bernoulli noise. There is a difference between the variance and the pseudo norm. One that scales like rho n, the other log rho n. So it's difficult to go from log rho n to rho n, but it can be done. Still, it's close to optimal in one of the regimes, not in all the regimes, and so we forward like trying to find something better, and like the natural candidate in statistics at least is the maximum likelihood estimator, right? We don't know what to do, right? So let's try maximum likelihood estimator. And actually, this is so natural in statistics, the maximum likelihood estimator for the stochastic block model or in homogeneous random ground model has been studied in several papers. This is not exhaustive list of works on that. The estimator will be also NP hard because we still have this problem of maximizing over all the labelings. But what is good about the maximum likelihood estimator, make it different compared to the least squares, there are computationally efficient approximations to this method that has been proposed in the literature and in different propositions, pseudo-likelihood method, variation approximation, and they are really successful in practice. People really use them, this approximation, and got some interesting results. And so next question, given that it's quite successful and we have this approximation, is the minimax maximum likelihood minimax optimal? And actually, yes, the answer is yes. We can prove an upper bound which match the lower bound with slightly more restrictive condition. Actually, the result is slightly worse with least squares. Why? Because we have a constant which will depend on the upper bound and the lower bound on the subnorm of the matrix. And so it will be minimax optimal only when the upper and lower bound, they are the same order. And if not, we can have exact formula for this constant to know how it will iterate the rate.
But isn't that more or less a problem we know for maximum likelihood estimators? Because if you, for example, if you had a bipartite graph, you have some probability 0 and the maximum likelihood will just never work because you divide somewhere by 0. So it seems that having problems when your thing is too near to 0 seems inherent for maximum likelihood.
Yeah. This is because like we have
whereas your least square doesn't have this problem, right?
Yeah, because we have log, right? And
right,
we need
exactly.
some Lipschitz condition on that. To go from likelihood to the Frobenius norm, we need Lipschitz condition, and this is how we get this constant. Yeah, I agree. But the good news is that we can prove for an approximation of the maximum likelihood that it is also minimax optimal, and there we don't need this condition on the smallest probability of connection. We can get rid of for this condition for approximation of this method. So maximum likelihood, at least what we proved, it was minimax optimal rate times a term which depends on both rho n and gamma n, lower bound. I can write it essentially gamma n square over rho n square, essentially that. And so it will be minimax optimal only when well, we know, right? It will be minimax optimal only when they are of the same order. But still, for a class of matrices, maximal likelihood is minimax optimal. Okay. But non-computationally feasible, still cannot use it in practice. And so actually the solution to this problem of maximal likelihood estimator that we cannot compute in practice, it's quite well known. So it goes through variational approximation. And on the first day of the workshop, we had very nice talk by Subabratak, who introduced the variational approximation. And so I just will somehow recap what he told. And so what is variational approximation? Variational approximation is the techniques which comes from Bayesian statistics, right? Which allows us to approximate the posterior distribution, essentially. In the first place, why do we need to approximate the posterior distribution? Because, so in statistics, we assume the data comes from a model. This model usually have unknown parameters, and they also may have latent variables, like here, like the labels. And the usual approach in Bayesian statistics, let's put a prior on the unknown parameters, and then let write the posterior distribution, so distribution of these unknown parameters given the data. But the bad news is that often we'll end up with hard to solve integrals. Okay, and so we have this hard to solve integrals, or optimization problem is here that we cannot solve. And so the idea, which comes from physics, I think, is, well, okay, I have this thing that I cannot compute. There is no analytical solution. Let's approximate it by something simpler. And this is called variation approximation. And as we are using approximation, we need to somehow measure how good we fit the true posterior to this approximation. And the usual choice is the Kullback-Leibler divergency. And still, often we end up with something that's quite difficult to compute, or there is no like exact analytical solution. And then the next simplification is, okay, let us assume that the distribution with which I will approximate my posterior can be written as kind of product, right? So I assume that these unknown variables can be somehow partitioned in a way that each partition is independent. And with this additional like simplification, then it is known as the mean field approximation. And after all these approximations, actually, why people are doing that, we often end up with something which can be computed, at least going through some interactive algorithms, right? And just to put it in perspective, when we have this posterior distribution that we cannot somehow compute the integrals, either we do this variation approximation, either MCMC, which can be slow, we try to somehow estimate this posterior. So this is one of two options that usually people use.
So just the previous slide, I guess I'm just missing something. No, I'm sorry, the next slide. The k to the n, so why can't one first find the communities and then estimate, you know, what is this k to the n?
This is all possible labelings.
But can't one come up with some separate pipeline which first estimates the communities reasonably well using the graph topology and then?
Yeah, but at least, so the only like, so the only results that I know in community detection, which provide us like the quite strong guarantees in community detection, which allows us to ensure that we are minimax optimal. They're restricted to very restricted cases. We have stochastic block model with two community, associative case, and so on. I'm not aware of any community detection method which works in quite general setting with good guarantees. So I can recover communities, but I need a guarantee on what I recovered. If not, I am not minimax optimal for fit to zero. You know, my main motivation, like to answer this question, is the computational gap. So I want to find the algorithm which is computational and minimax optimal for estimation fit to zero.
Okay.
So for sure, I can do it for some simple models, like two block, stochastic block model, associative case, blah, 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 same probabilities within all the communities.
So-
Once I outside of this case,
I mean, I would imagine if the degree n times rho n goes to infinity and you have like rank k or something, then somehow there is some I would have imagined, but presumably you can. That's why you need all this. But I just.
So one comment is, I think she also needs it for k changing with n, right? So most of the classical relations keep a fixed k, but she needs k changing with n as well. So it's just a comment mostly, but I think you are allowing for the possibility where k is possibly dependent on n. So the constants in your minimax result do not depend on either k or n. And the classical results are mostly for fixed k as far as I understand. So I think that's.
But somehow I fix also k because so it's in my set k
Right.
and rho and they are fixed.
It's fixed, but I think this result also applies if k is kn. If I remember Chow's paper correctly, but
I can let k grow with n.
Exactly.
Sure,
K could be log n.
There's no restriction
Exactly.
on k. Yeah.
Right. Thank
There's
you.
no restriction in this sense. Yes.
She wants to buy k depends on the errors, and if we have no idea how to do clustering, they have the exact correct k depends on the error on clustering.
The maximum likelihood estimator is always NP hard, but these spectral estimators are not Minimax optimal.
Okay, so just to finish with this recap. So fine, we don't know how to compute our estimator, later approximate it, so we can solve it. But what is about the statistical guarantees? Probably what we'll get in the end of the day, we're very far away from the true parameters. And the main point of Subabrata talks was that we think that in many situations, actually, variation approximation will be what he called accurate. That means that we'll end up in the ball of radius epsilon n with epsilon n which goes to 0. And he presented his result for linear regression. And if I need to resume my talk in one phrase, especially when I ran out of time, is that this mean field approximation works exceptionally well for the stochastic block model. It's not only like accurate, but minimax optimal, which is quite exceptional because people use a lot of variational approximation, but there is not that much study of its accuracy, except some specific models, in particular for stochastic block model. Okay, of course, we are not the first who discovered it, but variational approximation works pretty well in this situation. So I think first time that we proposed kind of variational approximation was in a paper by Dodin and co-authors. And then these two papers provided something quite strong guarantees on it. They provided asymptotic normality. So Celis and co-authors for dense case and Vikin and co-authors for the sparse case. And so we know that so we have asymptotic normality for variational approximation to MLE. And actually, people also use it for community detection. So there are some methods based on variational approximation community detection. And what we proved with Solen is that on top of this, what is known, it's optimal from a statistical point of view. The estimator that we are able to compute will be minimax optimal, and we don't need to know upper bound, lower bound, whatever. And what was like byproduct was not targeting it, but actually it also achieved under the conditions under which the model is identifiable, the perfect recovery of the labels. And this is a quite general setting. So people use it in practice, but they are right to use it because on top of being minimax optimal, it allows to recover the exact labels on the condition under which the model is identified. Okay, and so let me spend 5 minutes just to explain a little bit more. Can I? Okay, so first of all, as we're going for this variational approximation, we need to put a prior, right? And so, the stochastic block models, as I presented it in the beginning, it's usually called conditional stochastic block model, right? Where we assume that the labels are fixed, but the complete stochastic block model, we assume that these labels, they comes from a distribution, right? From a multinomial distribution with parameter alpha. So the prior on that. And so now we end up with stochastic block model of two parameters, the same matrix Q as before, and now the probabilities of belonging to each community. So this is the vector with k numbers, which one I pick a vector, and then I assign a community for this vector. So I'll assign my node to community I with probability alpha I. So this provides probability to be in the community I.
Prior on K as well?
No, K is fixed. No prior here. It's fixed. Okay, and so then we can write.
Is K fixed and known, or K is fixed now?
No. And so we can write the complete likelihood here for this model, right? Still summation over all possible labelings and be hard. And so we'll use mean field approximation. And here, what does it mean? It means that I'll approximate the posterior distribution of my labelings by a product of multinomial distribution. Like really like how can I put it? It's really like brute force, right? Like just everything is independent. It's let's put it in this way. Okay, and so and this approximation introduced me a new parameter tau, right, which contains these parameters for these multinomials in my approximation. Okay, and so what I'll do, so I cannot maximize the true likelihood and be hard. So I'll maximize it approximation. This is a lower bound. Why? Because this is the true likelihood. This is the measure how well I'll approximate the posterior with my. So this measure how far away is the true posterior from my approximation. And this Kullback label is non-negative. This is a lower bound. So I have a function that I cannot maximize. Let's try to maximize the lower bound, hoping that the maximum will be somehow close. Okay, because I not have that much time. Still, we have something like we maximize over 3 different parameters. Each one has like high dimensions. And so usual way how people do it in practice, they use kind of iterative algorithms. So let's fix 2 of these 3 parameters, learn the third one, and when we learn the third one, we iterate. And this is called expectation maximization algorithm by pretty standard in statistics. So it's iterative. Hopefully it's converge. And this is everything that is till this point is like was in the literature before us. What was known, in particular from these 2 papers, what was known with maximizing this lower bound is equivalent to maximizing the true likelihood, which is good, right? It was also known that the estimators for the alpha and q from this approximation will converge to 3 parameters. But there is no guarantees on the recovery for true labels. But actually, once we computed this variational approximation, right? We got alpha and q, but we also got this tau, which approximates the posterior of the labels. So why don't use this approximation to posterior for classifying the labels? And so this is what we did, right? Just take the maximum probability. So I'll assign a label to the community with the maximum probability from this approximation to true posterior. And once we have this label, estimator for the labels, actually what we did, we replace the estimator for matrix Q, which comes from variation approximation, by just the empirical mean. And these modifications allows us to get an estimator for Q for theta, which will be minimax optimal. So we need this modification, this trick, pass through the empirical mean to be minimax optimal. Okay, this is the result. We not be very sparse. We need to be a little bit. Yes.
Question. So, in general, I guess, the variational approximation may or may not have a unique global maximizer, right? For example, even in the context of linear regression, unless you assume something, it does not have a unique maximizer, global one. So in your setting, is there a unique global one?
So first of all, it's not for the solution of an algorithm for expectation minimization. It's really for the solution of a variational estimator.
Yeah.
And what they're saying, any point which will maximize my objective function will satisfy this conditions.
So you do not impose conditions which guarantee uniqueness of the global maximizer of one.
No, but somehow all the maximal will close.
So do you have examples in simulations where do you suspect that in this problem there is a unique maximizer, or do you suspect that there are multiple global maximizers in one?
Oh, this is a hard question.
We can talk later offline. That's
yeah, but somehow, what does it mean? It means that even if we have multiple maximum, that we're all quite close. Right? So we get exactly the rate what we wish under some conditions, and actually these conditions that comes from the paper by Bickel co-authors, they guarantees that the model is identifiable. If the models are not identifiable, we cannot identify the labels, so we cannot estimate my theta. And so we not only have that, so our estimator is minimax optimal. Somehow I missed the result. Yeah. We also prove that we achieve the exact recovery for labels. We can recover the labels. I'm surprised that I forgot to put it on the slide.
the constancy depends on the matrix Q naught.
Q naught, yes. But it's constant.
Oh.
When this certain, yeah, it's constant. That doesn't depend on rho n.
But the much larger depends on K.
Yes, sir.
So you need much larger than log n over n. So does this ratio?
No, it could be log of n. Just larger. It's like could be any log of n. Log n over n.
But you don't have uniformity K on that condition. So if you have larger K, it might have to be.
For rho n, you mean?
Yes.
On sparsity?
So you have a condition on this ratio to be sort of large. So while you need to go to infinity, probably it works once this is bigger than some 10 million, but 10 million could depend on K.
Here, this convergence.
Oh, you have this sequence. This.
It's just rho n can be any sequence which is it's just something. It depends on n and grows faster than log. So we need it could be log of n times log n over n. There is no k. Just because of some concentration results, we cannot deal with very sparse case.
So K could be n to the
It
5.
doesn't depend on k.
No, but
It's not just nothing to see with trivialization.
But C depends on Q naught and Q naught is the K, because Q naught is K by Q. So C depends on K.
Yeah, but it depends like on signal.
Also the infimum, right? Because you cannot take the entries of Q naught by zero.
But
Right.
not on k. There's no depend. So
Supremum and the infimum.
but first of all, I said correctly about two different questions. The constant and the sparsity. Right? So for me, sparsity level does not depend on k.
That was my question.
And here C Q depends on Q0, but only through like the signal, probably low. So maximum smallest values in Q0.
So both the soup and the inf, right? Because you cannot also let Q naught to be zero.
Yeah. Indeed, yeah, for sure. Okay, so let me just conclude. So we can extend it to the graphon model. We can estimate graphon model. It be minimax optimal. This is the rate for graphon estimation. Have something extra from there. Actually, it doesn't depend on our method of estimation. It's only depend how well can we approximate the graphon by the discretized version. So it's called agnostic error. It's also robust if we don't observe completely our graph. It's robust against the missing links, and it behaves quite nicely in practice. We try with real life data, but people did it before us because actually We have a variation of this variational maximum likelihood, but for instance, this package is variational maximum likelihood with slightly different estimator for Q. So it's also known, but it's reasonable in practice. Okay, so I think I should stop.
Increase.
Thank you. So I think it's interesting that in the sparsity regime where rho of n is order 1/n, that this mean field approximator doesn't work, and but that some other variational approaches do.
In the regime where rho n is of the order 1/n, which what our term says, that the zero estimator will be minimax optimal. We cannot do better than just put everything to zero.
Well, there's two regimes. I mean, there's when it's a sufficiently small constant times 1/n, depending on the parameters, then yes, there's nothing you can do. But then there's that phase transition, and above that, you can use things like belief propagation, and there are positive results by Massoulier and Massel, Niemann, and Sly, and so on. So, but I think it's interesting that there is some barrier here around log n/n, where we go from where somehow the posterior starts to really diverge from the product distribution, which is interesting.
No problem.
But my other question, which related to his, is that for the parameter learning, learning the matrix Q, and this is also just experience from that sparse regime, but in the detectable regime, there do often seem to be multiple optima that don't have the same likelihood. So if I understood you correctly, not for two groups, by the way, but if you have more than two groups. So for instance, if you have four groups, then sometimes a gradient ascent in this variational likelihood can get stuck at a local optimum, which is not as good as the global optimum because it's sort of dividing things the wrong way. So you made a claim that surprised me, which if I understood it correctly, was that all local optima of, so let's define a function f of q, which is the maximum of everything else but q. You said that in that, all local optima are equally good?
What I'm saying, this is for the original function. Now, I don't know how to find the maximum of this function. What I'm doing, I'm finding an approximation going through this exploitation maximization algorithm, right? I'm not guaranteed to get the maximum of the original function, right? But the second step here, I use an approximation to compute the maximum. Here I use the exploitation maximization algorithm, but there are many other choices. For instance, Lisa has a very nice paper on that. So then how you optimize it, right? But my results, they are about this estimator, which is computational in principle, but in practice, what we do, expectation, here what we use is expectation maximization, and actually probably it goes in the same direction. Actually, we need to like nice initialization. We use miss SBM to initialize our algorithm, and then it works quite nicely.
Okay, so it sounds like we both agree that if you don't have a reasonable initial guess from spectral algorithm that's popular,
yes, but
then you might get stuck
in this step. But all our results in discussion was about this estimator, because well, I need to compute it, and then I go through a second like layer of approximation. Okay. And did I agree with we need to initialize nicely? And what all simulations we did, we initialized with Mrs. BM, and it works pretty well.
I guess this is just a remark that maybe you make some identifiability assumptions under which you can recover what you're trying to recover. Maybe under those assumptions, all global maximizers are closed. So that's possible, right? Yeah. Maybe that's what your algorithm is benefiting from. Indeed. So there are some assumptions on the parameters which makes the model identifiable.
Yeah, but just remark. So our assumptions, the assumption under which your model is identifiable.
Right.
It comes from Bickel paper and so on. So.
Right. But maybe that's also what
Probably,
makes maybe that's also what makes the the variational approximation to have a, it could have multiple global maximizers, but all of them are maybe close. So then take any one, that would be a good estimate. Maybe, but that's. Oh.
Just curious if you've thought about extending your results to any of the extensions of the stochastic block model, especially the ones that have number of parameters.
Yeah, what we have is it's called Oracle inequalities. So we can prove that if your graph doesn't come from a stochastic block model, then with this algorithm, what you get, the risk will have this minimax rate with this BM, plus the Oracle part, which measure how far away your original graph is from a stochastic block model. And now we know, but taking large K, we can well approximate it. And so the question is, how large should be K?
Right.
But
I'm just more interested
Oracle
in actually estimating the parameters of these other more general models rather than just approximating them with a stochastic block model. But that's a different question.
Yeah. In a homogeneous random graph model, you cannot just estimate each parameter separately, right? Because you have one observation for Bernoulli distribution. Can I say about it? We need somehow group them to get something reasonable, or have several observations from the same model.
Right.
But only one observation from Bernoulli
it.
random variable. Tell me how to do it. Yeah, we have Oracle inequalities that depends how well stochastic block model approximate. It will approximate eventually well, but with large K. Yeah.
So I have a related question. So first, you have answers that. So if instead of a stochastic block model, you have a graphon, you get, in addition, you say the Oracle error, in other words, the best L2 error. So the best, in addition, you get the error, which would be the best lost model approximation, your graphon. I assume that's the Oracle error. Don't you also need something, how fast the graph converges to the graphon? Because if you don't have any other assumptions, it could be that the model, for the block model, we know it converges in some. So how, because in the end, now you don't want to estimate the matrix Aij, you want, I mean, Mij or Pij, you want to actually estimate the graphon, and for that you have to control how near Pij is to the graphon.
What we can say about the graphon model, right? So we want to estimate the graphon function, sparse graphon function. And actually it's quite simple to see from triangle inequality, but we'll have the error which comes from estimation of matrix, which you know how to deal with. And then we have this part, which called the agnostic error. And if you look at this part, it does not depend on my method of estimation. It's really how well can I approximate my graphon function by its discretization
So
at the
that's
random
all
points.
I wanted to know. So in addition to the Oracle error, you need the agnostic error.
Yeah, but this depends only on the class of graphon function.
Yeah,
it is known like this rates. It's known.
No, was not a. So I was just expecting that you need that.
But it does not depend on estimation methods.
I'm aware.
On the class of graphons.
So now to ask her question in a sort of more formal way, what if you had a degree corrected stochastic block model and I only have one parameter? I tell you that it's power law with parameter gamma.
Yeah.
So now I could ask you, so now you actually, it's a well-defined min-max problem. And so the question, reformulating her question is, could you estimate that?
We don't have results on that, but I think you can write the likelihood and then use variational approximation. I would expect working with quite well. And I think there are a lot of work on that. On the I think people have results on that. We didn't work on that, but.
Okay, so as one of the organizers, I want to finish by thanking all of you to actually now being willing to stay 15 minutes longer for our beautiful last talk. Thank you, not only all the speakers, but you as well for the wonderful questions.